All right, everybody. So welcome to another seminar in the open source hardware and EDA at UCSC. Today we have Pierre Emanuel Gaillardon. Is that how you say your last name?
Perfect.
He's an associate professor in ECE and adjunct in School of Computing at University of Utah. And he has an exciting project on open source FPGA fabrics, which I think is kind of a neat idea. So he's professor there. He does a lot of projects in EDA and so on. You know, you were at EPFL and so on. So come from there back over to the US, and you see him at all the major conferences, DAC, IC, CAD, DATE. He's everywhere. So that'll be my bio for you. Okay.
Thanks, Matt. Thank you very much for the intro. Yeah, it is funny. I mean, all the conferences, but I end up being mostly in the corridors more than the sessions because I never managed to get into the actual sessions. I always get stopped before, which is fun, right? That's the funny part. But all right. Well, thank you very much for inviting me to give an update about or a presentation and update about the work we do on OpenFPGA. As Matt mentioned, we have multiple projects revolving around open source hardware and software. This one in particular is sponsored by DARPA and has the objective of automating not only the prototyping, as a matter of fact, but the prototyping and production of standard and customizable FPGA fabrics and CAD tools. So what we recently did is actually going a lot beyond just, I would say, academic work, right? Because we are pushing all of that towards industrial tape-outs, working with industries in the Bay Area in transitioning our technology to their technologies. We have actually FPGA fabrics currently getting commercialized based on OpenFPGA. So it was really a lot of work, you know, beyond just this prototyping, but really looking into the production detail of that. So I'll hopefully, you know, give you a sense of all of that in this presentation. So let me get started first by why OpenFPGA and what is our main objective. So creating an FPGA is a tremendous task, right? What Xilinx and Altera does is very complicated. You have a bunch of customers, you have a bunch of target applications, and usually it requires a large team of senior architects and an army of hardware and software engineers to come up with production-ready layouts as well as the supporting CAD tools. Usually more than a year of development efforts, right? Definitely no easy task. The goal of OpenFPGA is to transform that model, and with a single architect, being able to create a complete fabric and its supporting CAD tools in less than 24 hours. So it relies heavily on automation. It relies heavily on high-level description languages to describe your fabric. And from there, the tool does its magic. What we achieved so far last year are 4 tape-outs with a very reduced academic team, right? So we taped out complete FPGAs and eFPGAs using 12-nanometer FinFET from GlobalFoundries, as well as Skywater 130 nanometers. We're supporting fully customizable modern architectures. We have more than 100 plus architectures are tested, ranging from low-end, low-cost, quote-unquote, fabrics, you know, ICE40, lattice ICE40-like fabrics, all the way up to fancy, fracturable, LUT6, Xilinx UltraScale Plus types of fabrics. And the entire framework was optimized for fast physical design. Creating a small FPGA prototype, academic prototype, is easy. Making an industrial fabric with more than 150 to 1 million LUTs requires significant innovations, and we're able to do that in less than 24 hours. So let me now dig into more details about the framework per se and how this framework is actually structured. So it is not an easy tool. It consists of many different bricks assembled together. What you can see on this figure is that we first rely on the combo Yosys VPR. Yosys and VPR are very well-known tools in the open source community. Yosys for handling behavioral synthesis, and VPR for architecture explorations of FPGAs. This is also what is used as core to SymbiFlow for supporting Xilinx 7 series FPGAs, right? So we rely on the same, underlying engines. But what we do is that we complemented this a duo by a few additional tools. The main one is what we call FPGA Verilog. The goal of FPGA Verilog is to take whatever representation that we can model with VPR and create complete RTL fabrics out of that, RTL netlists of the underlying system. So in order to do that, we had to complement the language from VPR with some, OpenFPGA architecture annotations and, more lower level descriptions compared to what VPR traditionally models. So we can do that all the way down to the nitty-gritty details of the circuit implementation. And we also support a complete test bench generator to validate that, whatever fabric we generate along with its bitstream generation actually matches and is actually correct. So we can, verify the complete fabric. In addition to that, we have also a bunch of stuff related to physical design right here with SDC constraints. So we generate the right timing constraints for the fabric, do some feed-through generation, physical design optimization and stuff like that to allow for this very fast implementation as I just mentioned. And finally, the bitstream. So if you look at this complex flow, we have two different branches that separates. The first one is about the chip design flow. So OpenFPGA is used to automate the manufacturing of an FPGA fabric, design of your fabric, implementation of your FPGA chip. And at the same time, we use the same framework to generate the end user design flow so we can distribute your chip and your tools to implement a bitstream to that fabric. And so we support both of that under the same software umbrella. So as I said, everything is integrated with the latest release of Yosys and VPR. So it is very strongly taking advantage of the large community revolving around these tools. And we created a shell-like interface around all of that to support very flexible design flows, very similar to what people do in commercial toolings, right? Where you have this TCL interpreter, making things very easy, right, for the users at the end to use our system. And we do have this separated architecture description infrastructure, so we can be portable across PDKs. So we somehow also decorrelate the notion of the architecture versus the low-level implementation. So it's very easy to port a given architecture to a 12 nanometer FinFET fabric or a 40 nanometer bulk technology. And finally, everything is, we have a lot of physical design oriented optimizations that helps us support all of that. So in addition to this core framework, we do support a large number of third-party tools, both from the open source and the commercial arena to make everything work. So one could think about different backends to implement our FPGA fabrics. We support tools from Synopsys, Cadence, OpenRoad. So we're able to implement our fabrics with all of those, semi-custom backend flows. Verification is handled again by, Icarus Verilog, Synopsys VCS, Mentor Graphics Model C, Synopsys Formality. We support all of those tools. And we validated, this approach with multiple PDKs, including advanced commercial, PDKs, GF12, and more relaxed technologies to, Skywater under 30 in particular. So how do we model an FPGA architecture? Well, the whole point here is that we want to be able to model an FPGA architecture, want to be able to model the architecture and its circuit components. And we do that using a high-level XML language. This XML language was not invented by us. We are using what VPR introduced a long time ago. Van Bet from the University of Toronto. It is a very well-known way of modeling FPGA architectures, very well used and mastered in the FPGA field. And so we just augmented that rather than going with a different route. So what you can see here is an architecture of an FPGA. So you have the island style architecture with your various blocks, configurable logic blocks, DSPs, block RAMs, and so on and so forth, right? With different levels of representation about what's inside of a given block. What you would note is that what our language allows us to do is to model things at a very low level. For example, if I go to a CLB that contains logic elements and fracturable LUTs, I know that as part of my logic elements, I will have a multiplexer that helps me switch between sequential or registered data or non-sequential path, right, to implement either flip-flop or not. Well, how do you do that? We want to say that your block right here is actually using a multiplexer, and this multiplexer is to be a one-level structure or a MUX tree or a two-level structure or whatever that is that you fancy for your FPGA architecture, right? But you're able to describe that at a very low level. Similarly, so that's created auto-generated block. Similarly, you could say that this flip-flop is actually going to be implemented from this Verilog file. So you can map it directly to some harder macros, right? Hard macros being a leaf cell, like a standard cell, to a flip-flop or something bigger. We also do support configuration protocols. So you can say, okay, I'd like you to implement a scan chain programmable programmation infrastructure for this FPGA. Bottom line being, this language helps you describe the FPGA architecture that you want. It does not do all the heavy lifting in generating a generic FPGA architecture. It still relies fully on the designer to say how the FPGA architecture should be. And that is actually one of the secrets to get high performance fabrics. One of the common mistakes that exist in other toolings is relying on behavioral descriptions. I have a LUT, and my LUT is supposed to work like that, and then give that to Design Compiler. Design Compiler will do something that is good enough, but you are not going to get the best performance. With our framework, you are able to say, I want to use this type of MUX. I want to use this type of buffers here and there, because you control the FPGA architecture. So it's simply a way to replace the tedious manual efforts of making full custom layouts and definitions yourself. The tool does that for you, but you still need to provide all those low-level details. So in addition to being fully customizable, we do support, so we do support many different modes. So for example, as I told you here, we can describe the MUX structure with a one level. We want to have input buffers that are there, no output buffers, that kind of thing. So you have very low level of control. At the same time, you can be user-defined, right? So this is a flip-flop that you take from my flip-flop.v, and this .v file contains whatever you want there, right? For whatever level of complexity. So you can have that. And in addition to just supporting this basic description, it supports the notion of multi-mode descriptions too. Let me give you an idea about that. So if you look at a real FPGA, commercial, 7 series FPGA from Xilinx, you have a fairly complicated basic logic element. It's a 6-input fracturable logic elements that is composed of multiple 2-input and 4-input LUTs that get reassembled together with some various multiplexers to, being able to implement either a 6-input LUT or 2 4-input LUTs or a full adder, that kind of stuff. What we need to do is to have the capability to model this physical view, but also tell our tooling that this physical block can be used in different modes. For example, it is typically used in arithmetic mode, where you just use this portion of the circuits and restrict the view, the goggles you put in saying this block as those elements. So when you map your logic to it, you only see those elements. Similarly, we can have 2 fully independent 4-input LUTs, and that will be the various blocks that are used. So we do support this notion of multi-mode, where we have ways to describe the physical description and the various logical modes and how they map one to another, which makes things possible for our tool to generate the bit stream accordingly. And this is all supported and fully automatic. So you just describe that in your XML architecture. The tool does its magic to support the final implementation. So we do have some built-in verification flow also as part of OpenFPGA. And verification is fundamental, right? You would definitely not want to tape out a chip without having it fully verified. How do you verify an FPGA? It's a tough task because FPGAs are undifferentiated fabrics when you manufacture them, and you need to make sure they are bug-free, right? It's not like a CPU. So how do we do that? We rely on a benchmarking effort where we take some benchmarks, we run them through OpenFPGA. OpenFPGA generates your FPGA fabric, the one you're going to tape out, and at the same time, the bit stream. And so we have a way to merge them together inside of an HDL simulator to make sure that the fabric you are manufacturing along with the bit stream generated by the tool do actually match the initial benchmark you wanted to implement. And we do that for a very large number of benchmarks covering many test cases, so to guarantee a decent enough coverage. In addition to doing functional verification like that, we also have a route where we have formal verification, so we can guarantee that our FPGA netlists, along with our bit stream, formally implement the input benchmarks. So we rely on Synopsys formality to do that. It works very well, except that formal verification is more bounded in terms of complexity, and we cannot really run that on very complex benchmarks. As a matter of fact, we crashed Synopsys formality. We ran out of its capacity, and we reported that to Synopsys, that is trying to patch it to support bigger fabrics. But so bottom line being, we have a very well defined verification framework as part of the tool, because this is fundamental pre-manufacturing, right? You need to have your fabrics fully verified. And that's what we have fully automated and part of our continuous integration. Now, post OpenFPGA, we have our complete physical design flow that is used to implement our fabrics. So as part of OpenFPGA, as I told you, we have the Verilog generation giving us netlists. We have design constraints, and we also have some TCL generations. So we generate our scripts to run the physical design tools. I'll only give you a quick run through on how things work. So the first thing we do is using our netlist and the various SDC constraints to implement inside of our custom backend tools, inside of our semi-custom backend tools to implement the fabric. So the constraints are here to constrain whatever input to output signals from the various blocks, so we get a good performance across the board. From there, we can obtain a complete FPGA fabric that implements our system. And now comes the question of signing off, right? Sign off. How can I sign off the performance of my fabric now that it's fully implemented? And we have two new SDC generators that come into the picture. The first one is going to exploit the Verilog plus complete SPEF exports from the actual fabrics to evaluate two things. The first thing we do is to do a benchmark timing analysis and an architecture timing analysis. On the architecture timing analysis, we have a bunch of SDC constraints that will just evaluate the performance of all the similar segments within the fabric. So you can come up with Gaussian distribution on where you stand, at various corners for your fabric. So, slow, slow, fast, fast, temperature corners and stuff. So you can understand the intrinsic performance of your fabric. That's one thing we do to guarantee that the fabric is high performance. The second thing we do is a benchmark timing analysis, where now we export SDC constraint that will constrain the right path within the fabric, so we can run a static timing analysis engine that will give us the performance of various paths within our fabric. Why doing that? And why is it so different than regular ASICs? Because FPGAs have loops all over the place. You cannot evaluate the performance of your fabric in a standard way using STA or using model sim. You need to provide constraints to cut the loops, extract the various timings you need, and reconstruct that. This is fundamental, otherwise none of your existing methodologies will work. That's what we do. That is part, again, of the framework to support all of that. All right, so that was a very broad overview of what the framework is. Now I'd like to just go through a couple of recent feature enhancements, just to show you more or less where we stand, and where we're going with that. So the first thing I'd like to mention is that OpenFPGA is fully written in C++ 2011 with a shell-like interface. So it's using a very modern implementation that is based on the latest VPR8 core engines. So it's really following what's going on in the in the community, and we do support that way all the work and efforts done by the University of Toronto or Google with SymbiFlow. So all of that is part of our effort. Very large build compatibility and very large CI implemented to that. So that was one of our focus for the past year. Cranking up the level in terms of software integration and code quality. I believe we're in a pretty good shape now. And obviously, as part of that, very significantly created some performance improvements. We massively improved runtime and peak memory for 100K plus LUT type of FPGAs. And we're at a point right now where it is actually very similar to commercial toolings. There is nothing to be ashamed with this open source framework to implement complex FPGAs. We're in the same ballpark as what Quartus does or Vivado does. The OpenFPGA shell is a recent introduction. So typically, this is what OpenFPGA was doing with the previous VPR. This is what SymbiFlow, to some extent, is doing as part of its CMake infrastructure. It makes things very ugly, right? With very long command lines and super hard to debug. So we adopted a command line interface and an iterative shell where people can just, write whatever commands they do, or have a TCL interpreter to just run the various portion of the tool in a very nice flow. So in the end, we are at the level of what a tool like Xilinx Vivado would do with their XSCT commands and shell interpreter. So you can just, type in your scripts, run your stuff, and get something of good quality. So easy to debug and to customize the flow functionality. One of our most important efforts right now is to go with higher versatility and heterogeneous FPGA architectures. So we support now multiple systems. So I/O capacity, so it's a number of I/O pins you get on the sides of your FPGAs. Previously, things were distributed uniformly. Now one can put, I/O pins on two sides of the fabric, nothing on top, or change the number of pins here and there. This is very important for eFPGAs. This is very important to implement also heterogeneous blocks and hard macros. For example, on this example, we are fully replacing I/O pins on the side of an FPGA fabric with a chiplet interface using the AIB standard. One could imagine to put PCI Express hard blocks, hard macros. All of that is doable in an automated way with OpenFPGA. Same goes for multi-column heterogeneous blocks. So to put, various sizes and aspect ratios for your VRAM, memory blocks, hard-coded, or hard macro processor elements inside of the FPGA fabric. So basically moving to an architecture that is more resembling to, Zinc or modern Versal types of architectures from Xilinx. We are heading towards that. Still a lot of work, but we are already in a pretty decent shape on that front. Configuration protocol. This is one of the big advantages of OpenFPGA. As I said, we are really interested in making good quality FPGA fabrics you can tape out. And configuration protocol has been traditionally overlooked in many other works, right? And we do support 4 different types of configuration peripherals, all coming with different trade-offs between configuration time, physical design, PPA, and whatnot. Just to give you an idea, so we do from low cost to high-end modern FPGAs, and I will not go to the details. I'm happy to talk about that, but configuration chain is just linking all your flip-flops, typically used in low-cost or small-size FPGAs and eFPGAs. We have memory banks. So you use an address and a row and column decoders to just address your various bit cells inside of the FPGA. Very well suited to emerging technologies, resistive RAM-based FPGAs that this infrastructure supports to, flash-based FPGAs, stuff like that. And finally, frame-based FPGAs. This is what Xilinx and Altera are currently using, where you do size your FPGA in different not segments, but regions that you can then address independently. So that makes things very versatile when you craft your architecture to put in the right system. We do support multiple configuration regions too, so we can load bitstream in multiple configuration regions. Here's an example. Instead of having a complete scan chain parsing through your implementation, you can have multi-heads configuration. So you load not only bits per bits, but words per words, the configuration into your FPGA. This is used in many eFPGAs to have very fast reconfiguration, for example. You could also have the same concept for memory banks. So you can split your column and row decoders in different regions and stuff like that. So why am I saying that? Because it's not only a hardware problem, it's a software problem. We need to have your bitstream to follow these kind of architectures. And OpenFPGA automatically does that for you, which is a nice feature. We have also a concept of fabric key. So with the goal of providing bitstream obfuscation and doing some hardware security. So as part of OpenFPGA, you can introduce what is called a fabric key if you prefer a unique identifier for OpenFPGA that needs to be provided to OpenFPGA to generate a correct bit stream for your fabric. So it's a way to just shuffle the flip-flops all over your chip, right? And if you do not have the right fabric key, the bit stream you generate will be incorrect. And this is particularly interesting and, of course, interesting to the US government, right? In creating more secured supply chains for FPGAs where you can manufacture an actual chip overseas, but nobody will be able to use it unless you get the right fabric key into your tooling to generate a proper bit stream. Having a fake key would result to a wrong bit stream, and it is very hard to reverse engineer the proper key because this depends on the size of your system, right? So obviously that concept does not really apply to very large, productions of FPGAs. But if you think about DoD-based eFPGA production and stuff like that, that makes a lot of sense, right? So you can really protect a small fabric compared to against some attackers. And the secured bit stream is done entirely again as part of the open source tooling. I will jump very quickly over these next 2 slides because they're not bringing much information, but we do support multi-clocks, right? And fancy clock generations, inverted clocks and all that kind of stuff. This is all part also of the system. I'll just jump over it. And design for test has been some recent features we integrated, right? Once again, manufacturing a fabric is great, but if you cannot test this fabric, whether it is for debug or more importantly for production, it is useless. So we took a great care about design for test, implementation of scan chain across fabrics, how to do that efficiently, and so on and so forth. So that brings me to another very important part of this talk, which is about the physical design enablements. Because again, generating a netlist, an RTL netlist of a fabric is cool, but pretty useless. What we want is to have good quality silicon out of this framework. And so one of the secrets is to use a hierarchical floor planning that enables scalable and customizable, shapes inside of our block and allows for what I call a top-level Lego assembly. So you can guarantee that the timings of your fabric are well controlled, no matter what the size of your system is, and that the runtime is controlled to implement that. So in addition to just controlling the or configuring the fabric, you do have IO-ring planning too, where you can really include at the early stage how your IOs should be distributed around your chip, including power supplies, accounting for IR drop, and those important physical implementation aspects. One of the important features of this floor planning is also the pre-generation of clock tree and signal routing. We want to maintain a tileable structure of the fabric, so we can, in the end, this block is exactly going to be the same block as this one, and I do not want to have non-symmetries inside of my system. So I don't want to have weird unique shapes. I need to account for some blocks. I need to generalize as much as I can the uniformity of the inequify of my system. And so that's important for and we do that by pre-routing an H3. We do that for scan chain and configuration routing, global signals going to each tile or going to each modules. So there is a lot of pre-processing and pre-planning to make that happen, right? But that turns out to be extremely powerful, because now we do basically all our design with a very small 2x2 FPGA. And from there, you can just Lego assemble fabrics of whatever size from these elements. This is very important because, and this is very unique again to FPGAs, because if you're using a standard methodology, which by the way is what other FPGA generator projects do, you get hit very quickly by an exponential wall coming from your design flow. If you look at a tool like ICC2, and because of all the loops you have in your FPGA and all the constraint in terms of routing and performance and symmetries, everything explodes very quickly, making fabrics as small as 2,000 LUTs to be infeasible runtime-wise. With our approach in pre-planning of clock trees and so on and so forth, we're able to significantly cut down this runtime and go with more than 100K LUTs in less than 24 hours, guaranteeing nice skew and nice latency across the complete fabric. And this is an illustration of a 164K LUT FPGA that we generated with our methodology. So this is a complete GDS view, right, where you recognize the tile I was just showing you in this picture, and you can see that everything gets very nicely, replicated in a tile, in a grid-based architecture, guaranteeing again good level of performance. Complete sign-off is handled or was handled in our various flows by commercial open source tools. I talked about that, but we have support of IRDrop, STA, DRC-LVS, all that kind of stuff is running nice and clean with our infrastructure. This was the highlight from last year. So we taped out a 12nm FinFET chip, heavily instrumented, very small design, but heavily instrumented. It's actually getting tested in my lab right now. So I don't have good result, except that we are just passing the power up sequence. So we're not burning anything, which is already a good sign, but we don't have any functional results just yet. It's going to happen in the next couple of days. We also did complete eFPGA implementation as part of the Google eFabless, MPW1 effort. Implementing a complete eFPGA based on standard cells, another one using custom cells, and another one using arithmetic cells. So full eFPGA is integrated with the RISC-V core. what was interesting here is that the 3 chips were built in 3 months by a 3-people team, which is very impressive to have this level of delivery and time to market, and it's only only possible with the automation that OpenFPGA provides. So I'd like to conclude with a final part of this talk, which is about the performance of those fabrics. And we have ways to actually make very high performance fabrics, considering that FPGAs are strongly made out of flip-flops and multiplexers. So there is a way not to rely only on standard cells, but create a handful of custom cells. That's what we're doing here in this example with the transmission gate, MUX2, and the configuration chain flip-flop that can then be used to significantly improve the performance of the system. So let me just show you here a graph showing an area estimation at the 40 nanometer tech node, TSMC 40 nanometer, of an FPGA implemented with OpenFPGA and comparison with the commercial Stratix 4. So the architecture is a Stratix 4 like CLB, and what we're seeing here is, so first of all, proper pre-planning and pushing the tools effort and stuff like that, brings us typically to a 2x bigger FPGA sizes compared to commercial FPGA, which is good, but from manufacturing perspective, the COGS would be very large in that case. But with our approach, that is a post-technology mapping approach and adding a couple of custom cells, we can really bring things down to an acceptable level. In that experiment that is already 2 years old, we were 55% bigger. Now we're almost on par in terms of sizes because one can just push further the tools. One can do some better, design shaping and whatnot. So we are bigger, but we're in the 10% bigger range, compared to what the commercial FPGA could be. If you look at performance, this table shows you the various timings you would get in the various elements of your FPGA, looking what OpenFPGA can do across multiple corners, typical, and slow, and what the Stratix 4 is telling us in its data sheet. What you can see is that OpenFPGA, again, gives you performances that are very close to what you would get with a full custom FPGA. So the bottom line here is that with our methodology in OpenFPGA, which is pre-planning of the various clocks, looking at low-level description of the architecture, use of a few custom cells, we're able to achieve not only good performance, but significantly cut down the time to market and rely heavily on automation. And at this point, I would like to conclude with just saying that so OpenFPGA, of course, is available on our GitHub with complete online documentation. We're trying to crank up big time the quality of tutorials and whatnot, but OpenFPGA is in a production ready state. Supporting various architectures, interactive user interface, and we're working, as I said, with a couple of commercial partners, and they're using OpenFPGA to create their next generation products right now. They actually just sent a tape out last week for a new generation of eFPGAs. It is significantly designed for time to market, 24-hour layout generation, 4 tape out with reduced teams. We demonstrate all of that. So we're very excited about these capabilities. Of course, I get the glory of talking about all of that, but that's really, a bunch of people who are working on that. So all the people from my team. And I like to mention Shifan Tang, who is a researcher and professor in my lab. We worked together for a very long time, and he is really the mastermind and lead architect behind the OpenFPGA infrastructure. So thank you very much for your attention. I'll be glad to take any questions you might have, but hopefully it gives you a good idea of what OpenFPGA is and its current capabilities.
I have one question about kind of the back when you were talking, yeah, good talk, by the way. Good kind of overview.
Thank you. No worries.
When you're talking about static timing of the fabric, wouldn't it make more sense to have it be more basically just characterization of the fabric? It's like you just, I don't know, it's not, you're basically have to characterize like a single kind of lookup table or things like that, and then you can abstract it from there rather than actually timing all of the paths through it. So it's a little different than digital design, right?
Mm-hmm. So we actually do two things. And, you know, it all depends on the methodology, right? So for sure, you need to, so you're perfectly right. So you need to evaluate. So as part of the static timing analysis, we do evaluate the performance inside of each blocks, right? So that's input to output of our CLBs. Then they're all the same because that's the exact same silicon going from one way to the other, right? So the same block duplicate all over the place, right? In addition to that, there are a few signals or a few parts that requires feed through that are not symmetric. So we deal, with just symmetries going that way. There is a little bit of top-level routing, very simple top-level routing, but that we sometimes want to account for. This is for that situation. And also, the way OpenFPGA is designed, that it supports this very high level of symmetries and design shaping, but it can also do everything flattened. As a side note, this is very important if you do things with open road, open lane, because open road, open lane right now do not support rectilinear shapes. So it is much better for density to implement your switch boxes at the top level in a flattened way. So in that case, you want to verify all your paths and stuff like that. So it really depends on how you approach your physical design and what you want to do. And here we have the ability to do all of that, for whatever makes sense. Does that answer your question, Matt?
Yeah, I think so. I was trying to promote Jose to a panelist. Another one of our faculty joined and he has his hand raised, but there we go. Okay.
Hello, do you hear me now?
Yes.
Hi. So great talk, I really enjoyed. So I have a question that, because you've been, I think in your flow you use mock turtle on the FPGA, on the synthesis, but there is the option of the ABC. And I'm curious, have you benchmarked, have you compared, how do they compare those things? Or do you see no difference or you have not benchmarked? Because there's the synthesis, there is the place, there is several options there here and there.
Absolutely. So, well, this is a very complex question, Jose, and I'll try to be as clear as I can on all of that. So OpenFPGA integrates as part of its flow UOSIS for behavioral synthesis. As a matter of fact, it also has a verific front end, right, for system verilog and stuff like that we're currently implementing and putting in. As part of UOSIS, it includes the ABC TechOptim. It also includes LS-Oracle as a UOSIS plugin. And inside of LS-Oracle, we do have mock turtle and also ABC re-implemented there. So bottom line being is that you can do pretty much whatever you want when it goes to logic synthesis. But now here's the problem. Evaluating a logic synthesis framework with an FPGA is always a complex beast. Why? Because FPGAs do have this notion of black boxes, right? You have these hardwired adders, for example, that very often are handled by at the behavioral synthesis level. So you look for your y equal to a plus b and say, oh, hey, that's an adder. Let me map that to it. And you basically bypass your logic synthesis step to do that. So, so that makes things harder to evaluate. Bottom line being, if we just look at the logic synthesis part, we evaluated what ABC can provide, what the MIGs could provide, and MIGs do provide interesting performance improvements on two things. The first thing would be reduced number of LUTs, increased performance, whatever that is for arithmetic intensive benchmarks. We knew that. The second stuff is that MIGs give you the ability to customize your architectures to support them in a better way. We had a paper a couple of years ago where we said, look, let's do an MIG-based optimization. Let's look for the critical paths and map those critical paths on the adder blocks in an FPGA, called the carry chain, basically. So we use the fast carry chain to implement the critical path. There's a lot of potential in that stuff. So MIGs demonstrate benefits, but we're not at a point yet where we are doing exactly what commercial toolings would do in terms of a behavioral synthesis, where you would look for your adders, transform them into a Boolean network, remassage them with mock turtle or whatever, and then bring things back through Boolean matching into the specialized resources. So there's a little bit of work there. However, we already demonstrated some interest in using MIGs for synthesis in this framework. Does that make sense? It's a very convoluted answer because it's it's considering so many parameters that it's hard to give you a firm answer.
Okay, yeah. At least you summarized how it was integrated. Thank you.
And in the end, when you look at logic synthesis in FPGAs, it is so tightly linked to physical design that makes things hard to decorrelate, right? You get a much better performance at your synthesis level, but you just exploded your fan out and timing inside of the fabric. So you need to make your fabric evolve. But then, is the synthesis better or is the fabric better? Hard to, get a fair answer to all of that.
All right. Do we have any questions from any students and the attendees?
So one question, and the students maybe are thinking something. If I were going to extend to a CG array kind of thing, so you have the FPGA frame, but then you start to add more coarse grain things. I guess I will have to have a new TMAP step. And this one, which one are you using for the TMAP? And I'm not so sure if the BPR will be able to handle. What are the things I will have to change in order to get something like that working on the flow?
Yeah, good question. Thank you, Rose, for asking that. So it really depends on your use model, right? On how you approach your CG array. You would so I would say the VTR portion is probably good enough, right? Because it will just be up to you to restrict your XML architecture for your CG array to make sure you route whatever signals from input A to output A to output to input B or stuff like that. In other words, you would, if I go back to, actually, let me just go back there real quick. Instead of describing this structure, one could imagine to have just block of the same size. And instead of going through the full details of how your blocks are implemented, you can just say, hey, this block is a processing element with a .v file that you provide yourself, and you just let VTR handle the routing between them. And that is perfectly doable, right? And supported right now by the tool. Technology mapping would be a little bit harder. It all depends on your use case. What do you map into your CG array, right? Are they ISA based or stuff like that? So very likely you would have to make things evolve compared to Yosis, ABC, whatever, LS Oracle, whatever that is, unless you can rely on their tech mapping framework and just map black boxes to it. Does that make sense again?
Yeah, yes, it makes sense. So you're using the ABC TMAP on the Yosis ABC TMAP. That's what you're using?
That's right. Actually, we're not really using the Yosys ABC TMAP. What we do is that we are using Yosys for behavioral synthesis, passing everything to LS Oracle to handle further level of optimization with MIGs and AIGs. And as part of that, we have our own TMAP on MIGs and the ABC TMAP on AIGs that we bring back together. But same principle. Flow map like, tech mapper, stuff like that. So,
okay.
Yeah.
I think there was one question in chat asking about the, a little more clarification about the bottleneck for the formal verification stuff.
Yeah. So without exactly knowing how formality handles things, right? Usually formal verification is based on, Boolean satisfiability and stuff like that, right? It's an NP-complete problem, right? It's very good in many cases, but it's still, an NP-complete issue. And if you look at the FPGA, well, actually, where we are is a good example, right? So think about a very large fabric, right? In a very large fabric, you have plenty of LUTs. In every single 4-input LUTs, you have a bunch of SRAMs plus routing multiplexer. That's a lot of logic cells and memory elements, right? That you have there. A lot of transistors, basically. And now you will want to formally verify that a 2-input AND gate that you are mapping onto this fabric is formally equivalent to this very large fabric programmed to be a 2-input AND gate, right? So you are creating a SAT problem that is extremely large because you need to evaluate all corner cases and everything. So it just scales, in an exponential way with the size of your fabric. So you basically very, very quickly just, reach the limits of what your formal verification engine can do. Does that make sense? So think about it compared to verifying a large ASIC or CPU, where every single gates are useful. In the FPGA, most of the gates are useless and not programmed. But you have to deal with that, super quickly. Does that make sense, Jason? It's essentially a memory problem and then a runtime problem, complexity problem, right?
I have a quick question, a little bit related. So in our case, we use formality and we use JOSIS for logical equivalent check. But most of the time we use JOSIS because it's a little bit faster, but in some cases it doesn't handle. So why didn't you use JOSIS on the logical equivalent check? Did you have some problems or you didn't try?
Or it just failed a lot quicker.
Okay.
It just it fails a lot quicker, probably 10 times quicker than formality in terms of, just scalability, runtime, and not runtime, but scalability of the problem you can feed into the tool.
Yeah, in my case, what I saw is that when it has flops, it has a problem. If it's pure combinational, it's a little faster.
That's right. That is correct. And in that case, it is full of flops, full of loops, full of plenty of nasty things that you would have, plenty of nasty things.
All right. Well, if there's no more questions, yeah, thank you for coming and spend the time with us. And it's an interesting talk. I'm amazed to see the progress this has made since I first heard about it. So it's a lot of stuff.
Yeah, we have a lot of things there.
Actually, one more question. Are you doing another tape out on the Skywater or?
Yes, so we're currently working on a few new tape outs. We are working on some heterogeneous tape outs. Heterogeneous with DSP plus homogeneous fabrics. You'll love that one. DSP plus OpenRAM plus homogeneous fabrics. So that's what our current objective is on Skywater. We're working on that. We're working on a ReRAM-based FPGA tape-out on Skywater 2. We're working on an Intel 20 nanometer FinFET tape-out. And on the UMC 20 nanometer, just a bulk tape-out. Quite a few tape-outs, as a matter of fact.
Yeah.
And obviously testing on whatever we did also last year, which is the most important at the moment.
But actually, it seems like after you get the testing set up, that should be pretty streamlined too, except for the new things like the new interfaces and so on. So
sure.
Yeah.
But at least, so we also, as part of that, we're building a low-cost test bed that will be also open sourced. So people who tape out stuff can then, easily test their fabrics and all that kind of stuff. So there's again, going the route of, whatever, silicon democratization, I guess, right? But providing more capabilities. Also, one maybe shameless plug, we recently created the open source FPGA Foundation, whose goal is to promote projects related to open source FPGA fabrics and open source FPGA tooling. We're going to have a lot of technical activities going on within this foundation. It's still getting started, but I invite everybody to go check out the osfpga.org, and hopefully we can all have an impact on the field.
All right. Well, we'll end there with the plug. Okay. Thanks again.
Thank you very much.